Experimental Mathematics Seminar. Today's speaker is Dr. Enya Guha, who will speak about this masterpiece, Insight into Game Theory. It's my favorite book. I recommend to everybody, and Enya will talk about it. Thank you. As usual, anybody who would like to join us for dinner is welcome, but they have to let me know the usual place, Evelyn, at 6:45 in the office. So let me know right after the talk whether you can make it. And one more announcement, everybody is welcome, but the seminar rules absolutely prohibit the use of laptops or smartphones or any other device. Thank you.
Thank you very much. My name is Enya, and I say a few words just before I'm starting. Then we have the slides, which will make for me easier. My English, please. I apologize about my English. You know, I came to the idea of game theory, or to write a book in game theory, from the point of view of a mathematics teacher at the high school. And as if I felt that there is something in the teaching of mathematics in high school that is so technical and so boring that we are losing many of the students. From not the bright one, because the bright one, it doesn't matter if there is a teacher or not, or if there is a book or not, but still, we have in Israel a very strong group in game theory, mainly because of Professor Oman, who is a Nobel laureate in game theory. And he's strong enough, and a very strong mathematician too, that the whole group of surrounding him is a very good one. And even here in the States, there are some of his students. And you know, in the community of game theory, there is a joke that says that if you want really to know game theory, it's better that you start studying Hebrew, because mainly the Israeli group of game theory is very big and very strong. So I came, and I'm not a game theorist proper, you know, I am not a proper researcher, but I came from the point of view of the teaching of mathematics and the teaching of game theory. So I came to it. The starting point was a book in Hebrew, and we thought and we hoped that it will go into the system, on the high school system, but as you can imagine, it didn't. We don't have enough teachers that are in the system to go into the system. I don't know exactly how it is here, but in the high schools it's very, very difficult. I tried, you know, I made some kind of a workshop with teachers, but it was really nothing. And then there is someone at the Stern Business School at NYU that he is an Israeli that is there, and he knew the book in Hebrew. And he said, look, there are many students who are coming for the first degree, even the business school, or sometimes even economy, that they are not oriented so much and not strong enough in mathematics, and they don't know anything about game theory. And you need to get some, so his, you know, idea was, we have to try to translate the book into English. And we took the mission, and it was translated into English, and was published by a very good publisher, Cambridge University Press. And since then, it was 2 years ago, or a little bit less, it was translated to Russian too. So there is, if someone is reading and speaking Russian, there is, I have a copy, but I don't know. We found someone, some of the guys from the center told me, you have to find someone who speaks English, speaks Russian, and knows game theory, otherwise it will not be even not similar to your book. Because he said he once was in Moscow and gave a lecture, so he was talking 5 minutes and the translator was talking 15 minutes. So he said, I don't know what he said. So we found a guy that is coming to Israel. We have a Institute of Advanced Study, they have every year in economics, school, summer school, and he's coming, so he knows English, he knows game theory, and he knows Russian, so he helped us with Russian. He went through it, and it was very nice of him. So in the meantime, I tried to Chinese, but there is no one really interested. Some editor told me that he's very interested, but then he said, well, not now. Anyway, so I wrote a book, and the book is a course, like a base for a course in game theory. To the level of high school it can be, and the level of college or whatever for students. So the
no, it's for everyone, even I enjoyed it.
For anyone.
Yeah. For even professional mathematicians were not experts.
Yeah, it is. And the name of the book is Insights into Game Theory, because it's not a proper textbook, a classical textbook in game theory. It's like to get a kind of a sense what game theory is. So here I am trying to
push twice because you have a blank page,
twice?
Remember?
At the middle?
The right one.
The right one.
Yeah.
Okay. A few branches of mathematics have been more influential in the social sciences than game theory. In recent years, it has become an essential tool for all social scientists studying the strategic behavior of competing individuals, firms, and countries. However, the mathematical complexity of game theory is often very intimidating for students who have only a basic understanding of mathematics. Here is offered a course in game theory which addresses this problem by providing students with an understanding of the key concepts and ideas of game theory without using formal mathematical notation. That was the main idea for me. Try to make as minimum that I could the formal language. So the course investigates 4 areas of game theory by using 4 different topics. By the way, everyone is a Nobel laureate. The first one, the college admission, it's a paper that was published, I think, in 1953, that is called Stable Marriage and College Admission by Gale and Shapley. Shapley is a Nobel laureate in game theory. David Gale passed away before, so he didn't get any. The other thing is social justice and majority voting, which the Nobel laureate here is Kenneth Arrow from Princeton. Coalitions and cooperative games, it's again Shapley value, so it's Shapley who is a Nobel laureate. And a bankruptcy problem from the Talmud. The Talmud is a Jewish ancient that 2,000 years ago was written by the Jewish, how you call it, scholars or whatever. And and it's also a kind of a Nobel laureate because it's a paper written by Professor Oman, who is a Nobel laureate in 2005. In the 21st century, game theory stands in the front of the interdisciplinary research, and yet the high school's mathematics curriculum ignores completely this branch of mathematics. Game theory undertakes to build mathematical models and draw conclusions from these models in connection with an interactive decision-making situation in which a group of people not necessarily sharing the same interests are required to make a decision. Mathematical modeling is the essence of the teaching of mathematics. The problem is that most of the mathematics taught at school has no connection to real-life situations, and therefore the mathematical modeling is quite meaningless. Game theory is a branch of mathematics that is motivated mostly by the social sciences, or better, by human behavior, and therefore constructing mathematical models for real-life situations is natural to the theory. In game theory, one can ensure that the students are able to understand the basic problem on which they are working. Our main goal was to make mathematics a subject that can be discussed and thought about through a basic comprehension of the problem at hand. So it will be an outline of the course, but I would like to say that it was written something about the interdisciplinary of the game theory. I'm coming from the Center of Rationality at the Hebrew University, which is unique in the world. What is very special in it is the core of the center is the mathematician, the game theorist. But around them, there are people from the law school, economics, biology, ecology, psychology, philosophy, you name it. So it's proper interdisciplinary, and there are many papers that are written in the center because of common work between the members of the center. So that's the outline of the course. The course follows the book Insight into Game Theory and Alternative Mathematical Experience, written by late Michael Maschler and by myself, published by Cambridge University Press in 2008. The choice of the topics reflects our purpose. We wanted to present material that does not require mathematical prerequisite and yet involves deep game theoretic ideas and some mathematical sophistication. Broadly speaking, the topics are all related to the various meanings that can be given to the concept of fair division. The course is a collection of few topics from the theory that are intended to open a window onto new and fascinating world of mathematical application to the social sciences. It selects a small number of topics and studies them in depth. It shows the student how mathematical model can be constructed for real-life issues. One of the aims of the course is to acquaint the students with different mathematics, a mathematics that is not buried under complicated formulas and yet contains deep mathematical thinking. Another aim is to show that mathematics can efficiently end social issues. The third aim is to deepen the mathematical thinking of the person who studies this book. We believe that by studying the topics of the book, the mathematical thinking of the student will be enriched. The book on which the course is based is divided into chapters that are independent so that the teacher and the student can choose one chapter or several and cover them in any order. The first chapter, mathematical matching, concerns, among other things, the problem of assigning applicants to institutions of higher learning. Each applicant ranks the universities in which he is applying according to his scale of preferences. The universities in turn rank the applicants for admission according to their own scale of preferences. The question is how to effect the matching between the applicants and the universities. The problem leads to unexpected solution. I would like also to make a remark here that there was a paper that was written by David Gale that he wrote that in 1960, I think, in the New Yorker, there was something written about the problems of admission to Yale University. So it was, in the paper, it was spread how it's complicated and how it's tough for the admission office to get the student, according to their preferences or whatever. And they were working, Gale and Chapley at the Rand Institute then, and they decided that they will try to find a kind of a solution that will start with a stable matching. Now it's called, I call it mathematical matching, but they call it the marriage problem, the marriage stable problem, and because it happened to be, they started talking about schools and students, but then to make it easier for the proof and for the, everything that, all definitions that we need, everything, it will be easier if the situation will be n student with n schools, which is very artificial, of course, means one student to one school. So what is really was going to be more similar to it is women and men, matching and women and men, and it will be one-to-one.
But there was in the old days, well,
yeah.
Men marry women.
Yeah, but that's now you can say everything. Still, you can say group A and group B. It's supposed to be groups, otherwise it's not. And they proved how, which is really very surprising, that there is always stable matching, which is not, the proof is very, very easy, and the situation is, it is surprising because any kind of, you take any preference you are writing for men and for women, and you are taking the all, even though at the beginning they made a kind of supposition, kind of that there will be no indifference and just one-to-one and just the same number. It's needed for the proof, but then you can generalize the problem, and it comes that even someone says, well, I'm staying alone, I'm going just with A, otherwise I'm alone. And it still works in every kind of situation, so which is very surprising. The second chapter, this is we call it social justice, concerns social decision rules. In a democratic society, it is customary to make decisions by a vote. The decisions supported by the majority of voters is adopted, as we know, from our society. But we show that majority rule does not always yield a clear-cut solution. The attempt to find other voting rules raises an unexpected difficulties. So, to tell this paper, it was written by Kenneth Aaron, I think it's in the 60s, And it's his theorem called the impossible theorem. So he took a kind of paradox, which called the Condorcet paradox, which is if you take a group of people and you write all the preference, the model of the paradox is 3 people with 3 issues, and then it comes, if you are working with a majority rule, that X is preferred on Y, is preferred on Z, is preferred on X, which is a circle that it cannot be. That means that it's not in every situation the majority rule will give us a solution. So what else tried to do, he drew a set of 5 axioms, trying to find a kind of a solution that will fulfill all 5 axioms. Let's say one of the main that I can say no dictatorship. And when you start looking for it and proving it, it says that every situation that you take, it will lead to a dictatorship. So it means that all 5 axioms are not fulfilled altogether. So that's the reason that he called it the impossible solution. So this is one of his, I think that even he got his Nobel Prize for this theorem. The 3rd chapter, the Shapley value in cooperative games, addresses, among other things, the following problem. A group of people come before an arbitrator and inform him of the expected profits of every subgroup, as well as the whole group, if the groups operate independently. It seems that these data are sufficient for the arbitrator to decide how to divide the profits if all litigants operate together. Now, the Shapley value, you know, it's this is one of the solutions for cooperative games. What makes it interesting, very interesting, it's an only one solution. Because there are, in game theory, there are situations that you get more than one situation. Game theory, in a way, it's not a descriptive theory, it's a normative theory. So you can say that in this situation, you can do A, B, or C, and you can choose. The Shapley value is a kind of a one and only one solution. So if you take a group of people and we are dividing, you know, the whole group to subgroups, and every subgroup gets a number of the worth of the subgroup. And what the Shapley value says, that if the big coalition is constructed, they are going all of them together, he gave only one solution how to divide between all the members, the number, you know, the essence, the state or whatever that they have together. So this is one of it, and we are showing it in many situations in a way like a situation of making cooperative in stuff like working together or building things together, and suddenly they are deciding to, you know, to split back, and so how they are dividing between themselves what they have together, and it is one solution. The first chapter, which is the analysis of a bankruptcy problem from the Talmud, addresses the following problem. Several creditors have claims to an estate, but the total amount of the claims exceeds the value of the estate. How should the estate be divided among creditors? In the chapter, several solutions are accepted, two of which are discussed in the Talmud. Now, in the Talmud, I'll show you. In the Talmud, there is a kind of a situation that there are three women married to one man, and he passed away. One woman was promised $400 dollars or whatever if he's passing away. The other one, 2,000. It's a kind of a traktat. In Hebrew, it's called the ketubah, between in a marriage, that the bride is saying that he will pay the broom. He will pay in case he's dying or whatever, what she wears for him, and 300. And the estate was, once it was 100, 200, and 300. So in case if the estate is 100, so it's smaller, this very small amount, the Mishnah in the Talmud says they will split it equally, which makes sense in a way. Now, the Talmud says she will get 50, and they both will get 75, which altogether is 200. And here it will be 50, 100, and 150. Now, if you look at this column, it's, the estate is very small, so they are splitting equally. Here, it's split, divided proportionally, which makes sense also. This is half of what she was promised, it is half of what, and this is half of what she was promised, and altogether it's 300. This column has no explanation along the whole debates of the Talmud through the 2,000 years ago. There was nothing that, there was kind of, hints or whatever, but nothing was really an explanation for this. So Professor Oman and Michael Maschler, they took this situation and they translated it to a cooperative game, and they found that the whole table is one of the solution of cooperative games that is called the kernel. Now the kernel was created, I think, in the 1969 or 70 by someone from Tel Aviv University. So probably the old Talmudic, guys, they didn't know anything in game theory. After they found the solution in game theory, they stepped backward and tried to find the kind of a solution that will make sense adapted to the times of the Talmud, which was very, very, very nice. And they generalized it, that the situation can be that the amount of the estate could be anything, and the number of the creditors can be also whatever it is, which brings something very surprising to the whole situation. So this chapter deals with a problem from the Talmud. Broadly speaking, all the chapters in the book represent attempts at reaching a decision in a conflict situation, and in each of them we show difficulties in trying to define a superior solution. The third chapter on the matching presents a weak condition of stability, which nevertheless yields many matchings. One of them is the best for the man, and another is the best for the woman. There is nothing that we can offer which is the best for the whole of both of them. There are situations that it comes that it will be the same if we are making according to the Gay-Shapley algorithm, it can be that both will get the same matching, and this is the only one. But it's not in general, so it cannot really be. The second chapter tries to reach a decision by voting, and we saw that the fair voting rule is not always possible, as I told you about the situation, the impossible theorem. The third chapter has probably the most successful solution, which is the Shapley value. It provides a solution for an unbiased arbitrator by supplying axioms that seem fair. However, somewhat different axioms not covered in this book yield different solutions. So it's not every situation can be covered with it. Finally, the fourth chapter, which considers a case of the bankruptcy conflict, shows that even in this simple case, a superior solution cannot be found. In conclusion, we see that various solutions are well tailored to many real situations, but there is no single solution that fits all situations. Each solution sheds some light on reality. I would like to add something too, a kind of a remark. I read a lot about it, and when I was writing my PhD thesis, that almost all the chapters, the social scientists were in a way upset about what game theory gave them. They were sure that they are getting models, mathematical models, and then they can use them, and it will be, a help to like in science. And they were quite frustrated because game theory doesn't give a specific solution every time or everywhere, and sometimes it gives more than one solution. So we have to say that's it.
Because human beings are much more complicated than particles.
Yeah, that's in physics you can make better than in social sciences. So that's it. Thank you. Any questions or whatever?
Very much. There's time for questions. So, was it ever adapted in class?
Yeah, in a way, I'm doing because I am a member of the Center for Rationality, we have two things. I'm running a kind of an experiment. It's a 6 year that we are doing it for high school kids in Jerusalem that are coming from high schools in the Jerusalem area, and once a week for almost a full academic year. We are starting when the academic year is starting, and we are finishing right now at Pesach. Before they have
for gifted students?
Yes, yes. They are coming for 3 hours once a week. We are teaching them game theory. I'm not a teacher, I'm just in charge of it. The teacher, at the beginning, they started, he made it pro bono, one of the professors of computer science, You know, he came after his post, Michael Shapira, and he was very keen to do it, you know, so 2 years he made it pro bono. And when he became very busy, his student, his PhD student in mathematics and computer science together, he is a teacher. And so they are studying, basically, this is the core of the course, but we are adding, you know, stuff. It depends on the kids. It depends, we are adding some material, so, and they are getting lectures, you know, like enrichment lectures by members of the Center for Rationality. A lecture in law, how we applicate the application of game theory to law, how it's the application to psychology, to economics. So once in a while they are getting a kind of another thing that we have a kind of a program in the center that students can take a track of a master degree and PhD degree in rationality. But they have to come, they have to be registered as PhD or master student in one of the subjects that there are members in the center. Means you can come from law, from economics, from mathematics, from computer science or whatever. They have to be registered there and fulfill their duties there. And they have to take some specific courses in our center. And one of them is game theory. Now, what we found that the course in game theory was given by pure mathematicians, and it was, you know, rigid and hard. So the students from economics or law school or other social sciences or other humanities parts, you know, even they were bright in their subject, they came to be a student in the Rationality Center. So there was, last year we started it. I took to do a course for them, which is light game theory, which is, you know, more based on my book, not very rigid mathematics, but kind of to open, you know, open the mind or whatever toward game theory, and then if they succeed or they want, they can take another one. But it is enough, and we decided that we are doing every 2 years. So last year I started, and next year I do it again. Within the basic is this: that I'm an expert to teach game theory for non-mathematicians. That's my expertise.
Yeah, I want to make a suggestion. It is such a beautiful book, but it deserves a part 2, second sequel. So we could do next equilibrium and
really? You think so?
So please write another book.
For the non-cooperative games.
Yeah. So did you ever think of writing a sequel?
I'm thinking, you know, but you know, it's first I need marshmallow, but you know, in a way, the reason that we made it for the cooperative game, starting with it, because it was meant to be in Hebrew for high school kids. And if you start with strategic games, you have to know a little bit of probability. And not all the students at the high school.
No, I'm not complaining why you didn't include it here.
So that
I'm
was
saying you should write another book.
Yeah. So maybe, so that was the reason that they skipped the whole nation, equilibrium and all the stuff.
Yeah.
But in the course that I'm teaching the students at the university, we are doing it too. You know, again, in a light mode or something, not very mathematical rigidity, but still we are doing it, yes.
Thanks again.
Anybody want to come? This would fit nicely for a 103 course.
Oh yeah, right. Oh yeah, maybe we should adapt it.
Show it to Michael Weindorf.
Oh yeah, we should show it to, I suggested. It fits in one of the courses taught in this
Really?
for non-mathematics majors?
I think that in general, for non-mathematical majors, it can make a lot.
Yeah.
Because I'm always talking about, a mathematics teacher, that I think that mathematics is important in schools because it's within the subject matter, it forces you to think, to think logically, which you are not getting used to it when you are studying humanities or even social sciences. And mathematics is it. And you can do, with game theory, you can do something which is, as I'm saying, light, but still very impressive in one way, and very attractive in other way, and still it's do what it's needed to do with the mathematics in it. Because I don't give anything, there is nothing that is not true in mathematics or non-mathematics, still mathematics, but it's given in another way.
Thank you. If you like your class for dinner, I decided to make it earlier than